Welcome to Molecular Biology and Biotechnology Glossary. This is Terminologies 101 with Lucy. We have been on a series of terminology starting with letter R. And I know, of course, we cannot exhaust all the words that start with R. So I just want to have a small change. We go to terminologies that begin with the letter B. And our very first terminology will be biomimicry or biomimicry. Yeah, it depends on where you come from or your English teacher, as we say. Biomimicry is the design and production of materials, structures, and systems that are modeled on biological entities and processes. It is some sort of nature-inspired production. Okay, so you use nature to design a material, to design a structure, or to design a certain system, because nature and biology already provide the mechanisms of action of those particular, maybe organisms, plants, etc., any living organism. An example is like this building in Zimbabwe. It is called the Eastgate Center, and it is inspired from termites, the way termites make their molds, like this one here. Usually they'll make them in such a way that they are self-ventilating and they are able to allow air in and air out, and of course that means a good temperature inside. So this area in Zimbabwe is very hot and it has extremely large external temperature fluctuations, and therefore they designed and constructed this building that passively self-regulates the building internal temperatures despite the very large external fluctuations. So you can see the way the building has been designed. It even has ventilations up here and also on the sides, and this is the internal structure. So usually when even there is wind, it will also utilize wind will come in and be able to sweep out the temperatures and the hot air and get it out, and this building usually having cool temperatures. Another area we are using biomimicry is in the transport industry, and this of course happened very many years ago. For example, the making of our aeroplanes using the eagle design, of course, because we have already seen the eagles fly very high and efficiently. So that was what was used to design these transport means. And also we have the Japanese bullet train that resembles the kingfisher beak, this beak here. And this train used to have challenges of speed as well as atmospheric pressure that used to also increase the vibrations and noise, particularly during tunnels. But now when they discovered this kingfisher and how it's able to move into the air, into the water, etc., they used this design, and now the train uses very little electricity. It is not noisy, and of course the speed has increased significantly. Then there's this challenge of needles and pricking and being injected and drawing of blood when we are sick or during other medical interventions. And of course we know how it can be difficult for some people who even have needle phobia. So the mosquito of course has an annoying ability to painlessly and unnoticeably suck our blood and of course get away with it, and maybe what we are left is some itchiness or maybe a small inflammation. But this has inspired Japanese scientists to create a hypodermic needle that is equally painless. What a joy for some of us. The key to less pain, of course, is the serrated proboscis of the mosquito, which reduces the surface area of the skin in which it enters. Now, I know there are many examples, and for those that are curious, I know you will look for as many examples in our setup, because there are extremely many: architecture, transport, landscaping, wind. I mean, almost every other industry uses biomimicry. So this is just a summary of how do we come up with structures, systems that have a biology or nature inspiration. The first thing is what we call to distill. So this is a design spiral. We start with distilling the design function. Instead of asking what do you want to design, we ask what do you want your design to do, so that now you look at nature and see the things that do what you'd want your design to do. Then translate to biology, that's identify the functions. Then ask how does nature do that function, what organism does that function. Then reframe your questions, of course, define the habitat conditions that reflect that design parameter, and then translate life's principles into your design. Then discover the natural made models. Go outside, of course, now survey, consider both literal and metaphorical models. Comb through literature, brainstorm even with experts and biologists, and create a taxonomy of life strategies. Emulate nature strategies, brainstorm multiple solutions. Now see what strategy and what solutions can you get. Refer back to the discover phase, and of course consider chimera designs. Then consult biological experts again. Go back to your model and explore as much strategy so that you can have a refined design. Then evaluate your design against the life principles. So now you have designed. Can your design adapt and evolve? Because of course any biological system does adapt and evolve to various changes. Does your design create conditions that are conducive to life? Yes, because we do not want anything destructive. So whatever design you come up with must also be environmental friendly. And how can you improve your design? Of course, even biological samples have limitations. So whatever you design can also be an improved version of whatever biological strategy you are applying. That's the design spiral. I hope this inspires you. You don't even have to be in biology. It could be mathematics, architecture, engineering, any STEM program, social, etc. Whatever area you are, maybe this is a challenge to do biomimicry.